Sorry. Yeah. So we'll be over p-adic reductive groups over either a finite extension of QP or FQ power series T. And we'll be interested in the group of rational points, which is a topological group. The topology was explained in the first Brouhardt's theory lecture. So we'll be interested in finite length smooth representations of such groups. Okay. So smoothness was also defined both today morning and on Monday. It just means that every vector has a compact open stabilizer. So for such representations are typically infinite dimensional, and therefore its character in the naive definition of the character does not generalize. However, you can view the character as a distribution. Namely, you look at all the locally constant, that's the infinity, compactly supported, that's the C, functions from the topological group G of F to C, set theoretic continuous smooth locally compactly supported functions from G of F to C. Given such a function, we can define what is theta pi of F. Okay, so a distribution is simply a linear map from this function space to C without any topological constraints, continuity constraint. Okay, so it's defined in the obvious way. You form the integral pi of F as usual, and then just take its trace. Okay, so these representations have a property called admissibility, which means that pi of F has finite rank. Therefore, it is an element of V star V dual tensor V. You can pair it and get the trace. Okay. So that's trace as a distribution. However, it is also true, though we will not need it quite for this lecture, that you can actually think of that distribution trace is actually a function trace. Okay, so this is a deep result of Harishchandra in characteristic 0. And a independent stunning recent proof which is characteristic free is there by Raphael Bosa-Plessy. Okay, so why characters? So first of all, they can be used to distinguish between representations. Secondly, they are very crucially used in a lot of applications. For instance, though the Arthur-Selberg trace formula is on adelic groups, its the way it pans out also involves local characters. Okay, and characters reflect several properties. For instance, the way, so you see the function theta pi from last page, this is locally constant on the set of regular semi-simple elements of G of F. Okay, but on other points such as the identity element, near such points, the character actually blows up. So it is not locally constant, it's only locally integrable near those points. So the growth of the character value near 1 actually tells you how large the k fixed vectors of pi grow as compact open subgroups k shrink to the identity. Okay, and then there are other properties that can be found. So what does it mean to say that theta pi grows near 1? There is a way to study asymptotics of such characters, and that involves, unsurprisingly, you pull the character down from the Lie group to the Lie algebra using an exponential map. Okay, so here U and V can be taken to be invariant under the G of F adjoint or conjugation action. Okay. So what you do is you restrict the character theta pi, the distribution character theta pi, to the open set V, and then using the exponential map, you just pull it back to U on the open neighborhood U of the 0 element of the Lie algebra. Okay. So, and then what do you do after pulling down? The general slogan is that the Lie algebra analog of a character is a Fourier transform of an orbital integral, and I'll define this in the next 2 slides. And why is this? Because if you have an abelian topological group, a character is simply an element of the Pontryagin dual. And the Pontryagin dual in these cases can be identified with the dual of the Lie algebra using an additive character. And the element of the Pontryagin dual defined by a character is just the Fourier transform. The Dirac measure at that point on the Pontryagin dual is the Fourier transform of the character. So let us discuss this in greater detail. So just like you define Fourier transform on finite dimensional real vector spaces, you can also define it on finite dimensional p-adic vector spaces once you choose a bilinear form. Okay, in this case, we want to study character not as an arbitrary distribution, but a conjugation invariant distribution. So we actually need G invariant harmonic analysis. That is why you take G invariant forms. So it's a slight modification of the Killing form. And secondly, just like you have exp of I times dot, you have an additive character psi. Okay, so this is color coded. So the point is that okay, so but a better perspective is actually to define the Fourier transform from functions on the Lie algebra to functions on the dual Lie algebra. Okay. Where instead of pairing x with y using a bilinear form, you just apply the element x of the dual to y. So it's more natural pairing. So what is happening here? So the Pontryagin dual of G can be identified with the dual Lie algebra using the character psi. Okay, so an element x in the dual Lie algebra corresponds to the Pontryagin dual element psi of x comma blank. And then the Fourier transform, usual Fourier transform from Pontryagin duality becomes this prescription. Okay? So this is what we will use. But for the purposes of this talk, those who do not like the dual Lie algebra can just take it to be the Lie algebra, because something like a killing form will allow you to think of the dual Lie algebra as the killing as the Lie algebra in a way which actually respects Brouhart-its Moy-Prasad filtrations if P is large enough. Okay, so this is Fourier transform at the level of functions. You also have a dual Fourier transform at the level of distributions. Okay, so usually if I use this magenta color, it means that I'm introducing a symbol. Often that symbol will be used in subsequent slides. So it's some sort of a signal that it's a good idea to remember that symbol. Okay, so we'll take distributions on the dual Lie algebra and pull them to distributions on the Lie algebra using this Fourier transform. Okay, so that is what Fourier transforms are. And now let us go to orbital integrals. So what is an orbit? Orbit is, you just take an element of G and then, take its orbit under the adjoint action of G of f. Okay, so orbital integral means you are just integrating a given function over the orbit. And what does that mean? You integrate over G of f modulo the stabilizer of x. Okay, so that's the usual thing. So integral G of f over Gx of f of this expression. Okay, if f is either f has characteristic 0 or if the residue characteristic p is sufficiently large, these orbital integrals are well defined because of two reasons. The first reason is that there is an invariant measure on G of f over Gx of f. And the reason is that G of f is automatically unimodular because G is reductive. Okay, and if x is any element of G, Gx of the centralizer of Gx actually happens to be unimodular in these situations because of SL2 theory. I mean, you can see that from SL2 theory, because they are algebraically unimodular and therefore unimodular as topological groups. So thus an invariant measure exists. That does not mean that this distribution makes sense, because if f is a function on the Lie algebra, there is no a priori reason why this should converge. Okay. However, Rangarao and maybe also Deline tells us that these integrals actually converge. So you are taking, oh sorry, this is a typo. It should have been the Lie algebra of f is in CC infinity of the Lie algebra of f. Okay, sorry about that. So f is in CC infinity of the Lie algebra. Its restriction to the orbit will usually not be compactly supported unless the orbit is semi-simple. So this integral is like an infinite sum, but Rangarao says that it still converges. Okay. And for us of particular interest is in the case where O is a nilpotent orbit. I'll explain what that means. Okay, so you see again this color magenta means that I'm going to use this notation later. Although O stands for a nilpotent orbit, O of 0 stands for the set of all nilpotent orbits. Okay, one knows them to be finitely many if P is large enough or if characteristic is 0. Okay, so this is equivalent to O being contained in the set of nilpotent elements. So this notation will also be used later. Okay, what does nilpotent element mean? You see, classically, a nilpotent element makes sense when you have a Lie algebra which you remember as the Lie algebra of a reductive group. Okay? A nilpotent element of a Lie algebra is an element whose Zariski closure, the Zariski closure of whose orbit has 0 in it. Okay, which means you can conjugate it so that it becomes arbitrarily close to 0. That's what a nilpotent element is. However, that classical notion is not suitable for these purposes because we are interested in harmonic analysis on G of f. Okay? But Moy and Prasad tell us what is the correct notion of nilpotent orbit to use. They say that an element is nilpotent in the Lie algebra if and only if it can be destabilized by a rational co-character over the ground field. It coincides with the original notion over perfect fields, but not over imperfect fields. Okay? But that also turns out to be equivalent to saying that if you look at the G of f orbit of that element, and you take the usual p-adic topology and take the closure, 0 should belong to it. Okay? So you take the classical definition, but replace the Zariski topology by the Hausdorff topology and G by G of f. Okay? So that's the definition of an nilpotent element. And this notation is also going to be used later. We'll have occasion to talk of all the distributions which are at G of f invariant and which are supported on the nilpotent set. We have already seen some such distributions, because whenever you have a nilpotent orbit, you know that the nilpotent orbital integral makes sense. So that is a distribution supported on the nilpotent set. Okay. So this is the space of all distributions, and in fact, these are all. That is, the space of distributions supported on the nilpotent set is simply spanned by the set of all nilpotent orbital integrals. You know, they are also linearly independent. Okay. So again, I'm keeping on assuming that the residue characteristic is large enough or characteristic is 0. Okay. So now these are not exactly what we are interested, but what we are interested in are the dual Lie algebra versions of these. Okay. But then you can think of G of f as G star of f for the purposes of this talk. Okay. So we are really interested in nilpotent orbital integrals on G star of f defined exactly similarly with an add star action. Okay. So I'll write O of 0 star for those nilpotent orbits, the collection of nilpotent orbits. Any question? Okay. Okay, so now we have defined Fourier transforms and nilpotent orbits. So we can talk about Fourier transforms of nilpotent orbital integrals. Okay. So, so again, remember what was our goal? Our goal was to study characters by using the exponential map to bring it down to a neighborhood of 0 in the Lie algebra. So the statement is that if you start with the character, you restrict it to an open open neighborhood of 1 in the group, and then bring it down to an open neighborhood of 0 in the Lie algebra. Or you can think of it as a distribution on the whole of the Lie algebra, which is supported on this open neighborhood. Okay. So you can also assume U to be closed. So that's why it's okay. Informally, we'll write little theta pi as the distribution on the Lie algebra, and we'll write it as capital theta pi composed with exponential, okay, in analogy with functions. Okay, so this is the theorem which was proved by Roger Howe and Harishchandra. It says that if U is sufficiently small, okay, so this is for characteristic 0. If U is sufficiently small, then little theta pi of f, okay, if f is supported in U, little theta pi of f is obtained by simply a linear, oh, this another typo, I should have written mu o hat of f here. Okay. So little theta pi coincides with a linear combination of Fourier transforms of orbital integrals on this small open set U near 0. Okay. So I said that the Lie algebra analog of characters is the Fourier transforms of orbital integrals, and this is saying that if you pull down a character to a neighborhood of 0 in the Lie algebra, you indeed get a sum of Fourier transforms of nilpotent orbital integrals. Okay, so these are nilpotent orbital integrals in G star. Okay, so in other words, little theta pi restricted to U belongs to the Fourier transform space of the space of distribution supported on the nilpotent cone, that is the span of nilpotent orbital integrals restricted to U. Okay, so this is just a rephrasing of this statement, nothing more. Okay, so here is a question of interest: how big can U be so that this characteristic expansion holds? Okay, so that is something on which Prasad theory shed a light, and so I'll come to that. So one might wonder, is this an ideal question? What does this buy you if you can prove such a thing? Okay. But it actually seems to be quite a fundamental property of harmonic analysis. And for instance, when Wolf-Poche shows that the fundamental lemma in characteristic 0 can be reduced to characteristic P, he uses analogous range of validity results, which are proved in very similar ways associated to orbital integrals. Okay, some slightly more refined versions. So this is actually not an ideal question at all. Yeah. Sorry? Closure of the orbit should contain 0. That's nilpotent. Yeah. No, I'm taking only those. Yeah, O of 0 star means the set of all nilpotent orbits in G star. No, but the question is outcome only. Yeah, so that's something on which Prasad theory is what gives a very conceptual explanation for that. Your conjecture. Okay, so maybe I'm. Yeah, but there are also asymptotic expansions where non-nilpotent orbital integrals show up, which are valid on slightly bigger ranges. Those are related to actually unrefined minimal K-types. Julie Kim developed such formulas, and they were further developed by Kim and Murnaghan. And Lawrence Price has recently done kind of very general expansions about arbitrary points and so on. Yeah. Okay, so let me give some idea of Harishchandra's approach, some really, really crude idea of Harishchandra's approach. Okay, so Harishchandra proves such an expansion not just for character distributions, but for a more general class of distributions called admissible distributions. Okay, namely, if K0 contained in G of F is a compact open subgroup with where pi has a K0 invariant vector. Okay, so this is going to be very important. Having fixed vectors under compacts is actually very related to having a character expansion. Then one of the first observations made by Harishchandra is that if you restrict pi to K0, you can decompose it as a direct sum of irreducible representations of K0, where each coefficient is finite by admissibility. Okay, and one can say what are the various psis that contribute to it. Okay, so Harishchandra's observation initially is that, or maybe Roger House, sorry, yeah, so I don't know, is that this is equal to 0 unless this psi has a fixed vector under a certain smaller compact open subgroup of this form. There should be some G in G of F such that G K0 G inverse intersection K0 fixes psi, fixes a vector, a non-zero vector in psi. Okay? So this looks like a very awkward condition. In fact, this is very almost trivial to prove. What is difficult is to extract any information out of it. Okay, so and that is where the nilpotence stuff comes in. Okay, so anyway, one can rephrase this condition in the following way. The fact that theta pi restricted to K0 has only certain characters can be rephrased as saying that theta pi star psi convolution is 0 unless psi has a certain fixed vector. Okay. Now, how do we possibly extract information out of this, right? Why is G K0 G inverse intersection K0 big enough to matter? Okay. So I'll not be able to give a very detailed explanation of that, but you can already see that Brouhardt's theory can be relevant to such questions, because yesterday we heard that any 2 points in a building lie in an apartment. So it can actually be used to study such questions. And one can also relate this to somehow to nilpotent elements in the dual Lie algebra. Okay? So somehow crudely the idea is the following. If theta satisfies that property, if a distribution theta satisfies that property, say theta pi, then we need to show that the descended distribution little theta is a linear combination of Fourier transforms of nilpotent orbital integrals, which is the same as saying that the Fourier transform of theta has support near the nilpotent cone. So that is what we need to show. Okay, so you need to show that something is a nilpotent orbital integral. You want to show that so it's a Fourier transform of a nilpotent orbital integral. You show that its Fourier transform is supported near the nilpotent cone. Okay, so somehow we need to go from here to here. Okay, so roughly this is the idea. Given pi with a K0 fixed vector, this gives information on pi restricted to K0, and we know what are the representations of the group K0. I mean, assuming that K0 is obtained by applying exponential map to a small enough lattice, Roger House Kirillov theory lets you relate the representation theory of K0 to the dual Lie algebra. Okay, so the point is that Kirillov theory is something that applies to nilpotent Lie groups, and groups like this are kind of pro-nilpotent. That's why you can expect such a description to be there. And that in turn gives information about theta pi near 1. That's a very, very crude idea of the strategy. Okay, so again, recall the question was that how big can U be so that this character expansion holds? Okay, so for that we need to, what are compact open what are open neighborhoods of the identity. We need to understand them. We need to have a handle on them. What sort of open neighborhoods of identity are under play? Yeah, sorry. Yeah. Yeah, so it is just a rephrasing of this in the language of convolutions. Okay, so the precise is not quite important for our purposes. So mostly I'll be talking only about characters, but whatever I talk about will have a version for admissible distributions. So that's all that I want to say. Yeah, any questions? Okay. Okay, so that was slightly technical, but we won't need the details of this slide in what follows. Okay. So now let us discuss compact open subgroups of G and open neighborhoods of G of F. Okay. So if X belongs to the enlarged Broughart-Ritz building of G, yesterday we saw that we have the parahoric subgroup associated to X. Okay. So you can think of the parahoric subgroup as G of F X comma 0. Okay. So Moy and Prasad define a further refinement of G of F X comma 0 as a decreasing filtration in non-negative real numbers of compact open subgroups of G of F. Okay. So these are denoted by G of F X comma R. So for instance, if G is GLN, X is the standard hyperspecial and R is an integer, it will be the principal concurrent subgroup. Okay. And similarly, there is a filtration of the Lie algebra and a dual Lie algebra, except that these filtrations are indexed by all real numbers. Okay, so we actually saw this in Jessica's talk today morning. She described how this works out for some points in the building of SL2. Okay, maybe the center of a chamber or something. Okay, so here is another example. If G is GLB over F, any point in the building is given by a decreasing filtration of lattices with some properties, and G of F X comma R is the set of all X in end of V, which takes the Sth lattice to S plus Rth lattice. Okay, so if R is large, S plus Rth lattice will be much smaller than Sth lattice, and therefore X will be much closer to the identity. Okay, so this is kind of like valuation of root datum, except that these are subgroups of entire G. Yeah, so the thing is, these are not good enough for to study character. These are not sufficient to study range of validity for character expansion, because these are not conjugate under closed under conjugation. If you conjugate G of F X comma R, you will land in G of F Gx comma R. Okay, so the natural thing to get a conjugation invariant thing is to take the union of all the G of F X comma R. So that's an open neighborhood of 1 in G of F, and similarly you have an open neighborhood of 0 in Lie algebra G of F, and similarly in the dual Lie algebra. Okay, so these are very nice regions. They are open, closed, and also invariant under conjugation or adjoint action as applicable. Okay, and these satisfy various nice properties, such as, although G of F R is the union of all the G of F X comma R, they are also an intersection of all the G of F X comma R plus nilpotents. Okay, somehow, so this is quite relevant to our considerations, though we will not explicitly use it because I will not get into the technicalities. But these are among the things that Moy-Prasad theory makes it available for us to understand neighborhoods of group and handle things. Okay, and if P is sufficiently large, exponential map always takes the Lie algebra filtration to the group filtration, and similarly with this open G invariant neighborhoods. Okay, and in fact, you don't need to restrict to the exponential map. For many groups, there are mock exponential maps which work. For GLN, you can take X goes to 1 plus X instead of the exponential map. For classical groups, you can take X goes to 1 plus X over 2 times 1 minus X over 2 inverse in outside characteristic 2 or residue characteristic 2. And Bezrukovnikov, Karzdan, and Warshawski have general logarithms that can take place of these. Okay, so then Jessica also introduced these today morning. G of F X comma R plus is whatever is slightly smaller than G of F X comma R. Namely, you take the union of every S greater than R. Remember, this was a decreasing filtration. So you take the union of all G of F X comma S with S greater than R. Okay, and similarly, you can define capital G of F X comma R plus as well. Okay, so this also we saw today morning in Jessica's talk, and this allows us to recall the definition of depth. Okay, so if you have an irreducible smooth representation pi, its depth is the smallest real number row of pi, such that pi has a non-zero fixed vector under some row of pi plus index Moy-Prasad subgroup. Okay, under some g of f x comma row of pi plus. Okay, so depth measures the first occurrence of fixed vectors. How large subgroups do you have which fix some non-zero vector in the representation? And it is unsurprisingly, even Harishchandra's proof relied on pi having fixed vectors under some compact open subgroup K naught. Okay, so this allows you to think of them in a more precise fashion. So, and here is the conjecture of Hales Moy-Prasad. If P is good enough, then the character expansion for the Lie algebra version of the character pulled back to the Lie algebra holds on this large domain G of f row of pi plus. Remember, this was the union of all the G of f x comma row of pi plus, where x varied over the building. So this is a open, closed, and conjugation invariant neighborhood of the of 0 in the Lie algebra. Okay, so it's a pretty large region, and the conjecture actually says that this is the range of validity. Okay, and if you actually look at the way depth is characterized in Moy-Prasad, this is actually a very natural thing to consider. If you try to look at G of f R for R equal to row of pi, you can see that the character expansion kind of fails because some semi-simple sort of element or non-nilpotent element comes. Okay, so and then De Backer shows that this conjecture is true if P is sufficiently large, depending on the absolute root datum of G. And more generally, this result applies not just to characters of irreducible representations, but also distributions which can be called R admissible. Okay. So now the rest of this slide and the next slide are slightly technical, but the thing is, the details will not be needed. I just want to point out some philosophical aspects of the strategy which will be relevant to us. Okay, so so you want to study the character by testing some functions on the character distribution. Okay, so the most basic functions to consider are characters on quotients of compact open subgroups like this. You look at G of f x comma R modulo G of f x comma R plus. Okay, and what does this hat stand for? Hat stands for Pontryagin dual. Okay, so one wants to look at characters of this group. You can think of them as locally constant, compactly supported functions on G of f. So you can apply, you can consider pi of psi, right? You can consider theta pi of psi. Okay, what are these other objects that I have written here? So first of all, I'm assuming that R is okay. So let us assume that R is positive. Then this quotient is actually an abelian group, and the logarithm takes it to the corresponding Lie algebra quotient. Okay, not just that, actually you don't need a logarithm. Moy and Prasad actually show that at the level of root subgroups, at least if the maximal torus of T is not terribly bad, you have a much more natural choice of this this isomorphism. So without even appealing to log, so this group can be identified with this group. Okay, therefore its Pontryagin dual can be identified with the Pontryagin dual of this group. How do you study the Pontryagin dual of this group? Remember that we used an additive character psi to identify the Pontryagin dual of the Lie algebra with the dual Lie algebra. If you choose that psi well enough, then the Pontryagin dual of this quotient can be identified with a corresponding quotient of the dual Lie algebra, where this R plus over here becomes the minus R here, and this R here becomes the minus R plus over there. Okay, so it should be trivial on the maximal ideal, but not on the ring of integers. Yeah. So that's actually that's according to how. So that's sort of how these filtrations are defined. You know. So, yeah. Okay. So yeah. So this is a natural setup to consider the questions like what we saw with Harishchandra's strategy earlier. So what Moy-Prasad show is that if R is greater than the depth of pi, and if this character psi of G of f x comma R occurs in pi, then what can you say about the corresponding coset in the dual Lie algebra? It has to meet the nilpotent cone. Okay, so this is how information can be extracted from the depth into something involving the nilpotent set. So that is, I hope, related to Professor Rajan's question.
Is given in what I mean, I'm just a good
Yeah. It is there in that. No. I mean, it's there in that book. Yeah. So this is how depth can be correlated to the dual Lie algebra. So it is saying, so it is kind of like saying the following. You see, it is the same as saying that if theta pi of psi is not equal to 0, or at the level of Fourier transforms, if little theta pi hat of the characteristic function of this coset is non-zero, then the coset should meet the nilpotent set. Okay. In other words, the Fourier transform of theta pi is supported near the nilpotent set, and that is how the nilpotent orbits kind of come in. Okay. So now, so this only studies the behavior of very specific psi. But to prove the character expansion, you will need to know the behavior of more general functions, but somehow that will need the exponential map. Okay, so I'll write the statement. It is slightly technical, but again, the details will not be needed. I just want to make two philosophical points about the technical statement. Namely, you can use this to study not just functions on the coset R modulo R plus, but also R modulo S plus with some S greater than or equal to R, so that you can study all functions which are supported in G of f x comma R for any x. So in other words, you can study functions in G of f R itself. That's the first comment. Second comment is that this statement is also saying that the Fourier transform of the Lie algebra distribution is kind of supported near the nilpotent set. Okay. So one is really interested in the restriction of the character to functions of this form. At the Fourier transform level, it becomes a more ugly set of functions, but those are what we need to study. And we need to study that show that the Fourier transform of the character distribution is supported near the nilpotent cone. Okay, so let me just summarize that. So I have just renamed R to minus R and S to minus S because we have Fourier transformed, so we don't want minuses around. So if you take T to be the Fourier transform of this distribution theta pi, okay, and we are thinking of it as a distribution on CC infinity of G of f minus R. Okay, why? Because minus R is our old R, and we wanted to study the character on G of f R. Okay, but we are now studying at the level of Fourier transform spaces, and this Fourier transform space, it's a very elementary check to see that this space has this description. Okay, what is this saying? If a function has a very small support, then its Fourier transform is invariant under a large lattice. Okay, so the smaller the support of the function, the more flatter the Fourier transform. That is what this is saying. Okay, so strictly speaking, this is just the set of all functions which are invariant under some G star of f x comma R plus, and you sum over all the x. Okay, you don't need the S, but somehow S is actually useful for the strategy. That's why you are keeping it. Okay, so whatever you have this Fourier transform space of Fourier transform of functions with small support. Okay, so this space is called dr. Again, this notation we are going to need. And on this Fourier transform space, we have observed in the previous slide some nice behavior. Okay, so I'm not going to recall that behavior again. So we have the Fourier transform distribution is defined on some weird set of functions, and it has some nice behavior. Okay, so let us call this this space J tilde R. Okay, it's the space of such distributions. So it is, let's call it the Walsh-Perget-de-Backer space, just for having a word for it. Okay, so what we need to show is that any such distribution is a linear combination of nilpotent orbital integrals on this space of functions. Okay, so what we need to show is that J tilde of R restricted to dr is J of n of G star. So these are the distributions supported on the nilpotent cone restricted to this space of functions. Okay, so sorry, that was a bit technical. Let me summarize what we did. We started with the character. We took R greater than the depth. We restricted the distribution character to a neighborhood of 0 in the Lie algebra. We took the Fourier transform, and we saw that Fourier transform had lots of nice properties. Okay, all the distributions that have those nice properties is the space J tilde of R, and this is the space of distributions which are supported in the nilpotent cone. This space is larger than that space, but when you restrict to this nice class of functions, these spaces are going to be equal. Okay, so that is the character expansion of Hove and Harishchandra. So the point is that if R is greater than rho of pi, I should have written, or sorry, if minus R is actually greater than rho of pi, then we needed to show that these two spaces are equal. Okay, I have just copied from the previous page. Okay, so I have just written n for n of G star. Okay, so there are some steps which are really easy. Okay, so so first of all, it is easy to show that any distribution supported on the nilpotent cone is actually contained in the bigger space of distributions J tilde of R. Okay, but these spaces are not equal because this space is very infinite dimensional. What we need to show is that when you restrict it to sufficiently invariant functions, those two spaces coincide. Okay, so that's the easy inclusion. Secondly, we already know, we observed in an earlier slide, that the distributions on the nilpotent cone, the invariant distributions on the nilpotent cone, have cardinality equal to the number of nilpotent orbits, okay, with basis as the nilpotent orbital integrals. So we know J of n very well, and we know its dimension. So what we need to show is that the dimension of J tilde of R restricted to dr is at most the number of nilpotent orbits. Okay, so that's a typo. I should have written the other O over there. Okay, calligraphic O. Okay, so we saw that the Fourier transform belongs to a certain space, and we need to bound the dimension of that space. Okay, so that's the situation right now. Okay, so the first step is the following. You see, this dr is a pretty nasty space. Okay, it is a sum over all s less than or equal to r. You don't want to deal with all of them. So the first step, and it's a very non-trivial observation of Roger Howe, is that you don't need to work with all the s over there. You just need to work with s equal to r. You can shrink dr to this smaller space and still preserve the dimension of this. Okay, so the thing is that J tilde of R restricted to dr to J tilde of R restricted to dr r plus is an isomorphism. Okay, so that's the thing. So the idea roughly is that you can use SL2 theory to actually replace this with slightly functions which are supported kind of closer to R plus, and kind of iterate that process. Okay, so it's a very involved and clever argument, and uses SL2 theory, which is one reason why we need P to be large enough. Okay? Yeah, so one more advantage of restricting to this space is that, here, if you look at the definition of J tilde of R, it was a very forbidding looking definition. However, on these functions, J tilde of R has a very nice description. J tilde of R is non-zero on a coset of G star of f x comma R plus, if and only if that coset contains a nilpotent element. So that way, you can hope to bound it by the number of nilpotent orbits. Okay. So the next step is to show that every element of this distribution space on this function space dr r plus is uniquely determined by its values on very specifically chosen cosets, where these cosets run over a set of representatives for nilpotent orbits. Okay, so the point is that every nilpotent orbit can be written as you can choose an element of a nilpotent orbit to contribute to this place dr r plus. Okay, but dr r plus vastly overcounts the number of nilpotent orbits, but then you are working with invariant distributions, and also which have this property that they are kind of supported close to the nilpotent cone. So using those two, you have to actually prune this dr r plus to a much smaller set of representatives for dr r plus, whose cardinality is exactly the space of dimension of the space of nilpotent orbits, and I have missed a star over here, and from that one can show that the dimension of this space is at most the number of nilpotent orbits in G star. Okay, so it's again a very clever argument, and the main point of this step is de Backer's classification of nilpotent orbits in terms of precisely such cosets. Okay, so so it's a kind of affine version of the Bala-Carter classification. I would have said more words about it, but I think I'll run out of time. So, so this is roughly the strategy of Walsh-Bourget and de Backer to prove the range of validity of character expansion. Okay, so if you prove this, you're showing that character expansion holds on G star of f r for every r greater than rho of pi, and therefore it holds on G star of f r rho of pi plus. Okay. So now the thing is, this is all done by Debacker, and we need to deal with spherical characters. Okay. So now we are going to kind of somewhat softer considerations. I need to recall what are spherical characters. Okay. So we do harmonic analysis on groups G in terms of characters of representations of G. Similarly, there is relative harmonic analysis, where instead of the group G, you think of G mod H as a G space, and the representations relevant to relative harmonic analysis are those representations of G which have an H fixed vector, okay, under the smallest subgroup. Okay. So this is the abstract setting. So how do you do character theory in this setting? Okay. So let me define a spherical character. A spherical character is not associated to a representation of G, but a representation of G pi together with an H fixed vector and an H fixed covector. Okay. So if you have these data, what is the associated spherical character? It is just the matrix coefficient associated to this vector and covector. Okay. So it is just you take G to pi of G acting on the vector and then pair it with the covector. Okay. So because the vector and covector were H fixed, this is not just a function on G, it is bi-invariant under H. Okay. But rather than as a bi-invariant function on H, it is more helpful to think of it as an H-invariant function on G mod H. Okay. So let me give an example of, so before that, let me just mention, here L being an element H fixed vector of V check is equivalent to L being an H-invariant function along V, and similarly L check is an H-invariant function along V check. Okay. So this is what is actually more appropriate for smooth representation theory, because for smooth representations, it is easy to get H-invariant functionals, but not H-invariant vectors, just like for CC infinity of G of f. You don't have an G invariant vector, but you have G invariant element of the dual, namely the Haar integral. Okay. Okay, so here is an example of a spherical character. You know, why this definition? So there is what is called the group case, where you take the group G to be H cross H and H to be the diagonal subgroup of G. Okay, so you can look at G mod H on which H acts from the left, and it so turns out that that is isomorphic to H, with where this action of H becomes conjugation, namely H1 comma H2 maps to H1 H2 inverse. Okay, so here, what is an H representation of G with H fixed vector? It is of the form sigma tensor sigma check, where sigma is a representation of H, where sigma check is a dual of sigma, and its dual is actually sigma check tensor sigma. And what can you take L and L check as? You see, these are you need such H invariant pairings. You can take them to be the obvious pairing between sigma and sigma check, or sigma check and sigma. Okay. So if you take this specific example, what is the spherical character you get? You can compute that the spherical character you get on G mod H. Okay, so remember, G mod H is identified with H. So as a conjugation invariant function on H, it is simply the character of the original representation sigma. Okay. So this relative harmonic analysis generalizes usual harmonic analysis, and what one might hope is that if you have a theorem on harmonic analysis, once you figure out the correct way to generalize to relative harmonic analysis, you can get papers for free. But it doesn't always work that way. Sorry. Sorry. Yeah. Yeah. Yeah, so our setting, we are not working with finite groups, we are working with p-adic groups. So p-adic symmetric spaces actually. So I want to choose H between G theta, theta fixed vectors in G, and the identity component of G theta. Okay, so any group will do. Okay, so for this we need the relative harmonic analysis, and I have to assume that P is not equal to 2 here, or at least characteristic is 0. So you can split G as the one eigenspace and the minus eigenspace of theta, and the one eigenspace of theta is nothing but the Lie algebra of H. Whatever remains, the minus one eigenspace is what you call P. Okay, so it has an action, adjoint action by H, because H acts on G preserving H, and this is simply the derivative of the action of H on G mod H. Okay, and let pi be a smooth finite length representation of G. And since I'm running out of time, let me just say that the earlier definition of the spherical character generalizes in an obvious manner. If you start with any representation and two H invariant functionals, respectively on V and V check. Okay, so it is just like you are taking a matrix coefficient, except there is a small subtlety here. You are taking the linear dual here and not the smooth dual, but still this pairing makes sense because this presence of this phi actually mollifies L check into an element. It smoothens L check. Okay, so one can define a spherical character in this context, and just like in the finite group case, it is an H of F invariant distribution on G of F. In other words, it's an H of F invariant distribution on G of F mod H of F. Okay, so Rader and Rallis in 1996 showed that in characteristic 0, you have a local character expansion at the tangent space of G of F mod H of F at the identity, which can be identified with this P of F. Okay, so earlier we considered the Lie algebra with the adjoint action of G. Now you are considering this P. This is the -1 eigenspace with the adjoint action of H instead. Okay, so Rader and Rallis showed that exactly a similar form of the character expansion holds in this setting if the characteristic of the field is 0. Okay, though some other properties like local integrability of characters fails, something still holds in symmetric spaces. Okay, so these are analogs of the set of nilpotent orbits, because it was a kind of invariant theoretic thing, so you can make those same definitions in this context as well. Okay, so again we have Moy-Prasad domains here. So recall that G of F was H of F plus P of F, and the building of H can be identified as the theta fixed points in the building of G by the work of Prasad and Yu. Okay, and when P is not equal to 2, you can show that this decomposition respects the Moy-Prasad filtrations for points inside B of H. Okay, so if you intersect P of F with G of F x comma r, whatever you get, you are defining it to be P of F x comma r. Okay, so you get analogs for symmetric spaces of Moy-Prasad filtration sublattices. Okay, and then just like in the group case, you can define P of F r to be the union of P of F x comma r. Exponential map will take it to a neighborhood of G of F mod H of F. Okay, the identity coset, and then using the spherical character here, you can descend it down via the exponential map to this set P of F r. Okay, so everything is exactly as in the group case, and then the hope is that the spherical character pulled down to the Lie algebra is a sum of Fourier transforms of nilpotent orbital integrals. Okay, so that is one is hoping for the exact same range of validity for the character expansion. Okay, so we are not able to yet prove this in the most general case, even with P far greater than 0. So let me say what we can prove. So just like in the group case, you see we have this more complicated space of distributions, the larger space. We can cut down the dimension of the larger space to exactly the number of nilpotent orbits. Okay, so the step that one might think is difficult is the easy step. I mean, easy step in the sense the group case is involved. One can mostly follow the group case. One has to, of course, relate Moy-Prasad theory for G and H and so on. Okay, but the dimension of the distribution supported on the nilpotent cone may be strictly less than the number of nilpotent orbits. Okay. This is because of two reasons. Unlike in the group case, there may not be an invariant measure on nilpotent orbits because the stabilizers, may not be unimodular. Okay. The second reason is that even if there is an invariant measure, Rangarau's theorem might fail. That is, orbital integrals may not converge. Okay, so this is the second reason. When these two issues don't arise, and one has some sort of a table or classification or something of when these issues don't arise, and when P is far greater than 0, then we have the expected range of validity result. Okay. In rank 1 situations, so these are the rank 1 situations. Although these failures do exist, one can still establish the expected range of validity result using either features particular to rank 1, or combining those with some sort of direct computation. Okay. So in rank 1 cases, somehow despite so many other things failing, the range of validity still seems to hold. So we have a hope that it might generalize to higher rank. So that seems, hopeful, but so we don't have a general approach to proving it. But let me make a few remarks to end. So a lot of the structure theoretic results regarding lattices, nilpotents, etc. in Moy-Prasad theory is actually very general. If you have a rational representation V and a suitable collection of lattices, etc., many of those results actually work well in that setting. But when you want to connect to harmonic analysis on G of f, of course, we need to specialize to our special situation. You want to relate nilpotence for the symmetric space and the nilpotence for the Lie algebra. I mean, okay, sorry, that is well known, but you need this at the level of quotients between R and R plus. Okay, so and then the analog of de Backer's classification of nilpotent orbits is already known. Ricardo Portilla or Portilla, I don't know how it is pronounced. So he uses, so just like de Backer worked with the building of G, Portilla uses the building of H, but with polysimplicial structure inherited from the building of G. Okay, so this work of Portilla is a crucial input for us, and then SL2 theory is really crucial for all these computations, but one knows that normalized SL2 triplets exist when P is greater than 0, namely to say that M, if you take an element, nilpotent element in the symmetric space P of f, you can actually complete it to an SL2 triplet so that the neutral guy belongs to H of f. So somehow that makes it possible to adapt many of the computations. Okay. So any questions?
You told about this regular points of GF, right?
Yeah.
In the beginning, the character functions are defined in that.
Yeah,
so the
regular semi-simple points actually. Yeah.
I mean, those are not nilpotents, or those
are never nilpotent. Yeah. I mean, first of all, they are on the group, right? Not on the Lie algebra. Yeah. Yeah. So when you pull them down to the Lie algebra using the logarithm map, they'll be regular semi-simple also. Yeah. And therefore, those are far from nilpotent. Yes. And rightly so, because you know that the characters are locally constant there. Yeah. Yeah. So, but all the asymptotics concerns the nilpotent elements somehow. Yeah. So one philosophical reason for why nilpotent orbits arise seem to be that if you look at the quotient map from G to the G modulo G by the conjugation, the fiber over 0 is the nilpotent set, and somehow you are pushing forward, and supposedly this has something to do with that, but I don't know how to make that theory into practice.
Another thing is that you told about the closure of the nilpotent orbits.
Yeah.
So there will be 0, but
they should contain 0. That's the definition.
As a limit point, but other than 0, is there any element which can be?
Yeah, because if you take so the nilpotent orbits are actually ordered. You can say that one nilpotent orbit is less than, actually partially ordered. One nilpotent orbit can be less than another nilpotent orbit if the first one is contained in the closure of the other. But so the closure of a nilpotent orbit will be a union of smaller nilpotent orbits. Yeah. Yeah. So maybe I should have also mentioned that actually I'm kind of embarrassed to say that I only noticed today that Lemaire has some work where Rangarao type results are adapted to characteristic P, where instead of considering nilpotent orbits, he considers nilpotent strata motivated by Hesselink, and there Rangarao type results are proved. So that might help us too, but so this might become outdated. I don't know.
So that you're increasing the domain of this validity and.
No, there is an expected domain of validity. One is trying to realize that. De Backer, yeah. So we cannot improve de Backer because in some sense de Backer is optimal.
Optimal.
Yeah. Thank you.